Welcome to the deep dive. Today, we are wrestling with what is, arguably the biggest structural anomaly in modern machine learning.
The scaling gap in reinforcement learning.
Exactly. We're deep diving into the paper, 1,000 layer networks for self-supervised RL. Scaling depth can enable new goal-reaching capabilities.
And for those of you steeped in ML, data science, and mathematics, you know the context here is everything. Our mission is to give you a really precise, comprehensive overview of what the authors did.
Right, no speculation. It's just the methodology, the stabilization techniques, and of course the remarkable results they got by pushing RL and network depth way further than anyone really has before.
And that structural anomaly you mentioned, that's the core tension.
It really is. You look at the rest of the ML world, large language models like Llama 3 or these huge vision models.
Hundreds of layers routinely.
Hundreds. Scaling depth is just the established path. That's how you get emerging capabilities.
And yet traditional RL has been stubbornly stuck in the shallow end. I mean, we're talking 2, maybe 5 layers max.
So the conventional wisdom has always been that going deeper is just a recipe for disaster.
Total instability, vanishing gradients, training failure, especially with the sparse, delayed feedback you get in most RL environments.
So the open question was simple, but profound. If you could solve those stability issues, could you unlock those same performance leaps in RL that, basically revolutionized NLP and vision?
And they answered that question right out of the gate. The core conclusion is, well, it's unambiguous. It's a yes.
It's a straight up yes.
Straight up yes. Scaling network depth, specifically up to 124 layers in their experiments, it delivered monumental performance boosts in unsupervised goal-conditioned RL.
Monumental is a strong word.
We mean gains ranging from 2 times up to an astonishing 50 times improvement in some environments.
That 50 times number, it just feels, it feels almost aggressive. It sounds like a claim that depth is all you need. But historically, the biggest hurdle in RL has always been that sparse feedback problem. So how did they fundamentally sidestep the issues that always plagued deep RL networks?
They realized that to stabilize deep learning, you need dense, high-quality gradient signals, and sparse RL rewards they can't provide that.
Okay.
So the breakthrough wasn't some brand new RL algorithm. It was marrying RL with self-supervised learning principles. They needed a system where the network could just learn representations constantly.
So let's unpack that. To get to this unprecedented scale, they outline 3 essential building blocks that had to work together. What were those pieces?
Okay, so first, the algorithm choice. It had to be inherently robust to that sparse feedback and really good for representation learning. They chose contrastive RL or CRL.
A self-supervised algorithm.
Exactly. Second, they needed data acceleration. They couldn't rely on these small, slow data buffers, so they used modern GPU-accelerated RL frameworks like JAX GCRL to get massive data throughput.
And the third component, I assume, was just the sheer network depth itself.
Right, going up to 100 times deeper than what you'd see in the traditional baselines.
But you can't just stack layers and pray for stability.
No. Absolutely not. We all know that dramatically increasing depth usually brings on these crippling gradient headaches.
So what did they borrow from the wider deep learning world to keep this 1,000-layer architecture stable?
Well, this is where it shows RL is finally, catching up to large-scale ML engineering. They integrated 3 standard but essential techniques.
Okay.
First, residual connections. You have to have them for effective gradient propagation. Second, layer normalization, which helps keep the activations stable. And third, they found the swish activation function worked much better for this extreme depth than, say, the traditional ReLU.
And the authors stress that you need all 3.
Yeah.
Take one away and the whole thing breaks.
It's a package deal. The scaling just falls apart otherwise.
That makes perfect sense. You need that architectural discipline. Okay, let's get into the algorithmic core. We're talking online, goal-conditioned RL. How does contrastive RL actually define the problem?
So in this setting, the agent is exploring, collecting trajectories, and it's trying to learn how to reach any future state you might command. The key move in CRL is how they repurpose the Q function, the critic. Instead of estimating some long-term discounted reward, the critic, this phi, becomes a measure of distance.
A distance metric based on learned embeddings.
Precisely. It's just the Taylor norm distance between a state action embedding and the goal embedding. So the closer your state action pair is to the goal representation, the lower the distance.
Which means a higher Q value in this context.
You got it.
But how do you train that critic robustly without the sparse rewards. That's the core problem.
And that's where the InfoNC objective comes in. It's a self-supervision engine here.
Right.
InfoNC basically acts as a generalization of cross-entropy loss. It reframes the whole training process into a classification task.
A classification task? How?
It's simple, really. Is the current state, action, and goal tuple? Was it sampled from the same successful trajectory? Or is it just some random negative pair?
Ah, I see. So by turning the value problem into a classification problem, you borrow all the stability that comes with classification losses.
That's a massive win for stabilizing deep training. Exactly right. And once that contrastive critic is learned, the policy is just trained to maximize it. It drives the agent towards state-action pairs that match the goal.
Let's quickly define the architecture, because the paper talks a lot about residual blocks. How are they actually quantifying depth?
They set a very specific standard. Both the actor and the critic networks use these residual blocks. Each block has 4 units: a dense layer, layer norm, and then the swish activation.
Okay.
So network depth is just the total number of dense layers across all of those blocks.
Meaning if you have n residual blocks, the actual depth is 4 times n.
Correct. So when they talk about a depth 256 network, we're talking about 64 of these blocks stacked on top of each other. That's 256 dense layers.
And that jump from a traditional 4-layer baseline is, well, it's massive.
And the results show it paid off in spades.
Let's get into those empirical findings, because the sheer size of the performance jump is where this paper really makes its claim. What did they see?
The quantitative scalability was it was undeniable. Across manipulation, navigation, locomotion. All of them.
What kind of numbers are we talking?
On the manipulation tasks, reaching and pushing, they saw solid 2 to 5 times gains. But in the long horizon navigation, like the ant mazes,
Yeah.
over 20 times improvement. Truly staggering.
And the most profound gains were where?
Those were saved for the humanoid tasks. They have the largest observation space, 268 dimensions.
Okay.
And there they got over a 50 times improvement compared to the shallow baselines.
50 times. So it seems like the benefit of deep capacity scales non-linearly with the complexity of the problem.
That's a great way to put it. And we should stress, this wasn't just some minor optimization. Scaling CRL achieved state-of-the-art results. It beat all the standard baselines, SC, TD3 plus HR, all of them, in 8 out of the 10 tasks they tested.
What's really fascinating, though, isn't just the final number. It's how the performance scaled. You said it wasn't a smooth curve.
No, not at all. They repeatedly observed this phenomenon of critical depth.
Critical depth.
Yeah, where performance would just suddenly, abruptly jump once a specific capacity threshold was crossed.
That's the signal we look for in scaling laws, isn't it? That sudden phase transition. We see it with emergent behavior in LLMs.
Exactly. On the ant big maze, for instance, that jump happened around 8 layers. But for the super complex humanoid U-maze, the critical depth was much higher. It kicked in around 64 layers.
And once they hit that threshold, the agents didn't just get better, they got different.
They learned entirely new ways of solving the problem.
And those emergent capabilities are the biggest hook here. Let's slow down and really detail what happened in those humanoid tasks as the depth increased.
The contrast is phenomenal. The shallow networks at depth 4 could only manage these, rudimentary policies. They'd collapse or flail or just throw themselves around.
Right.
At depth 16, the agent gained basic stability. It learned how to walk upright, move predictably.
But the really novel stuff, the emergent behavior, that came at depth 256 in the humanoid U-maze. What did those policies look like?
We saw behaviors that looked genuinely acrobatic, strategic. The environment had this high wall the agent needed to cross.
Right.
The deep agent learned to fold its body forward into this leveraged position and essentially vault itself over the wall.
Wow.
And even more surprising, it learned another strategy, shifting into a seated, low-profile posture and then worming its way over the obstacle. A highly complex, multi-stage maneuver.
These are not just slightly better versions of walking. These are completely unique emergent solutions.
Exactly. The shallow networks simply couldn't express that kind of complex, long-horizon dynamic.
And they pushed it all the way to 1,000 layers.
All the way up to 1024 in the humanoid U-maze, and performance just kept improving substantially.
So we've established depth is effective, but a lot of prior work in RL focused on scaling with making those few layers much wider. Which scaling axis won out here?
This is so critical for how you allocate resources. They confirm that scaling width is helpful. Going up to 48 units at depth 4 did improve things, which is consistent with other work, but depth was the dominant, more effective axis.
Can you give a specific comparison?
Sure. They showed that simply doubling the depth to 8 while keeping the width pretty modest at 256 consistently outperformed the absolute widest 4-layer networks they tested.
And that leads to a huge computational efficiency argument, doesn't it?
It absolutely does. When you think about parameter count, scaling depth can be way more efficient. They had this striking comparison.
Yeah.
Their widest, shallowest network depth 4 with 2048 took about 35 million parameters.
Okay.
In contrast, a much better performing, deeper network depth 32 with 256 only needed about 2 million parameters.
That's a massive difference. It suggests depth might be the more resource-efficient path.
It really could be.
Now let's talk about the subnetworks. Previous attempts at scaling often found that scaling the actor too aggressively could actually hurt performance. Did they see that here?
No, and this is another key finding. In contrast to that prior work, they found that scaling both the actor and the critic jointly was beneficial. Now, the critic scaling was generally more impactful since it's doing the heavy lifting on representation learning. But in some environments, like Ant Big Maze, scaling the actor actually gave a bigger gain than scaling the critic alone.
Which suggests you need depth not just for value estimation, but for expressing complex policies too.
Precisely. They work together. And another area where RL has lagged is batch size. Large batches are key in vision and language, but RL has struggled to use them.
Right, the classic problem where large batches just dilute the signal for shallow networks.
Well, the deep architecture solved this. Shallow networks at depth 4 got only marginal benefits from bigger batches. But as the depth grew, say to 64 layers, scaling the batch size became highly effective. It unlocked substantial further gains.
The deeper network can actually use the information in that bigger batch.
It can effectively use the reduced gradient variance.
But we have to keep stressing this. These benefits are tied specifically to the CRL algorithm and their architecture, right? This isn't a universal RL finding.
100%. They explicitly confirmed this. They ran TD-based methods like SAC and TD3 plus H or R with the same deep architectures. Performance saturated or even got worse beyond depth 4. Those algorithms simply can't harness the capacity.
One last check on methods. Did they try this in the offline setting, where the data is fixed?
They did some preliminary experiments. In the offline goal condition setting, they found little evidence of improvement from depth scaling. Often performance even declined.
So this is really about the synergy you get in online training.
It seems to heavily rely on the high-quality data being generated by the deep collector itself.
Okay, so if depth is the key, we need to understand why. Mechanistically, what is happening?
It all comes down to the power of the representation. When they visualized the learned Q function in a maze environment, the shallow depth 4 network was, well, it was naive. It relied almost entirely on simple Euclidean distance to the goal.
Which is guaranteed to fail if there's a wall in the way.
Exactly. It completely fails to respect the environment's topology. But the deep depth 64Q function, it learned these radically richer representations.
What did that look like?
The visualization showed high Q values that meticulously mapped out the actual physical path required to navigate the maze. The deep network encoded the corners, the constraints, the whole layout into its representation space.
And that better representation requires better data to learn from, which brings us back to the synergy between the deep learner and the deep collector.
It's what they call the exploration expressivity synergy. They designed an experiment to pull these two effects apart. And they showed that a deep learner only crushed a shallow one when both were trained on data collected by a deep network data with good coverage.
So if you train the deep learner on data from a shallow, poor explorer,
it struggles. It proves you need both. You need the capacity to learn and you need the capacity to generate quality data to learn from. Depth gives you both.
The way the deeper networks manage their internal representations is also really insightful.
Yes, especially near the goal state. When they visualized the embeddings, they found that shallow networks would cluster the states near the goal really tightly together.
Oh.
The deep networks, in contrast, spread out the representations near the goal. This suggests they're prioritizing distinguishing between critical goal-relevant states. They're allocating more representational capacity where it's needed most.
And that powerful representation translated into better generalization through something they called stitching.
Exactly. They trained agents in a maze using only short horizon goal pairs, so the agent only ever saw how to get, say, 3 units away.
Right.
But when they evaluated on complex long horizon goals 6 units, completely unseen, The Depth 64 networks excelled. They could stitch together those short experiences to solve the much harder long horizon task.
A capability the shallow networks just didn't have.
It was severely limited.
This whole body of work really provides the clearest blueprint we've seen for how to scale self-supervised RL. It decisively shifts the conversation. Depth isn't a constraint for this kind of RL. It's the dominant scaling axis.
It enables systems that can train their own large models and show those exciting emergent capabilities that, until now, we've really only seen in vision and language.
It proves the potential. But the authors were also very candid about the main limitation.
The compute cost.
Right. Scaling depth came at a significant cost. Wall clock time increased about linearly with depth.
It did. So the final provocative thought for you to consider is this. Given that these emergent behaviors and these 50 times performance gains are so incredibly valuable, how can we integrate resource-saving techniques?
Like what? Distributed training.
Exactly. Distributed training, architectural pruning, maybe knowledge distillation. How can we integrate those with these now validated deep architectures to systematically drive down the computational cost while absolutely preserving the amazing benefits of massive network depth?